Happy Easter, first of all, and welcome to this episode number 7 of this series, learning Amiga Assembly 68K with Docster. So I'm going to go quickly through the usual things, and then we can start with our thing, of 68K assembly. So where is the browser? There you go. So as always, please like and subscribe to my YouTube channel. This helps me in in making YouTube, showing my videos more to others. Hello Dario, hello Pelicus, and of course hello Hound Dog. Happy Easter to both. I do not see anyone else, but yeah. Hello Nanni. Say hello Nanni. Welcome to the stream. Basically, we stream for since you are new here, I stream normally Amiga stuff. I stream how to code to the Amiga using assembly. You're still digesting Easter lunch. So yeah, ciao to everyone and happy Easter. Buona Pasqua. So remember that under each video you can click the show more and you will see more information related to the video, and normally there is code like this one, the source code, that you can go and get it from the Mega shared drive. Please join, sorry, not join, follow and like my Facebook page. It's my blog right now, but this will change sooner or later. Eventually I want to have my own blog. On Facebook there is the Phase 101 group. Please join and follow, and also there's the Commodore Dev Facebook group. Please join and follow and like, whatever. This is where most of the stuff goes. Let's say that Phase 101 is for things related to Phase 101, and Commodore Dev is for anything related to Commodore, basically. If you send me a message on Facebook, I do reply, but I take long. However, if you come on Discord, I reply much more quicker. For those that do not like Facebook or Discord, you can also join Telegram. This week I did some changes to Patreon and Coffee. Well, Coffee I'm not ready yet, but Patreon, yes. So for those that want to go that extra mile and support us, you can support us on Patreon or Coffee. You will unlock 101, and that is not, it's a coincidence, 101 videos for you to related to demo coding, or sorry, not demo coding, related to Amiga coding or C64 coding. And yeah, the only thing that the enhancement that I did is that now you can, before it's very difficult to find the videos, for example, of a series. Let's say you want to find the series, let's make an Amiga game, okay? it was very difficult to track them. Now you just find the tag, you click on it, and it will show you all the series. Same thing as I said, we have coffee. I haven't finished organizing this, but it's the same thing. There is a copy of each of the same thing on both. So same amount of stuff. Some people prefer coffee, some people prefer Patreon, whichever. More than happy whichever you like. But I mean, you're supporting me, so I cannot be more grateful than that. For those that do not know, I have this page which has links to various things so that you can get you to coding. I've been advertising this page for quite a long time now, but yeah. Just exclamation mark book page, and it should get you to this page in the chat if you do not have it. But yeah. I am using from time to time the EC68K assembler in this series. Okay, it's a Windows thing, so if you're using Mac or Linux, it will not work, but there is something similar called 68000 simulator, which you can use. And with that, I jump to my Amiga. So this is the first example. We're going to go through the add instruction of the 68000. The reason why I'm going through it is because last time I did not have the intention of doing the add command, but I still did it, and I did it in a very quick way just to start this section basically. But now I'm going to go into more detail. As you can see, what it does is source plus destination are added together, and the result is into destination. Okay, that's how it works. The syntax is add some value to a data register or data register to an effective address. Okay, so it depends. Okay, what EA can be. It can work on size of byte, word, and long word. Okay, and it depends on the result. All those flags can be changed. Okay, so what you see there, so negative flag, zero flag, overflow flag, carry flag, and extended bit. Normally C and X are a copy of each other. Okay, so let's go through the example. So we move 1000 hex into the 0, so we should see that, and then we move it's a word, by the way, and we move a word also of 101 into the 1, so you see it there. Then we move that long number into the 2, which you see it also there in the debugging screen. Now we're going to add D2 with the 0, sorry, D1 with the 0, which you saw it, and notice it was a byte what we did. So because of that, we only copied the 01 in the 1, and we added it to the 0 and in the byte, so it became only 1001 and not 1101. Okay, because we were working on bytes. Now we're going to add D2 with D0. So D2, that number 1, 2, 3, 4, 5, 6, 8, with D0. So the 5 will become a 6 and the 8 will become a 1. Sorry, a 9. Now we're going to add D1, so the 101 with D2. And we see that the 6 becomes a 7 and the 8 becomes a 9. Ciao, back to the bit. Ciao Sam. Buona Pasqua. Guys, follow Sam if you're interested in games related to the Commodore 64, VIC-20, Apple II. He is the first one that I saw streaming of with Apple II, which I somehow like. Although I didn't know that the Apple II had so many games, to be honest. And also he does, if not mistaken, also NES. And sometimes Spectrum also, no? So, we continue with D1 to D2, and you will see that the number in D2, remember D2 is the destination, changed. As I said, the 6 became 7 and the 8 became 9, so we end up with 1, 2, 3, 4, 5, 7, 7, 9. Now we're going to move, and notice it's a byte into D0. Okay, so D0, the 7, 9 is going to end up with FF, and now we are going to move byte. It's because of the text, it went to the other side, I guess. D2 to with D0. So D2, the one that ends with 779 with D0. And there you go. Okay. So that was our first example, and this was the add. Let's do this next one. Today, it's like the keyboard doesn't want to work. So we are experimenting. Now we are going, this is an example of add address. So add A. Okay, so the destination is an address. Always, okay? We do not need to write the add A. Okay, as I said, the assembler will do it for us. So AD. So we move 102 into the 1. We move the 1, 2, 3, 4, 5, 6, 7, 8 into the 2. And we move the 400 into 80. We are going to move, now this is a word, not a long word, the 1000 into A1. Okay, we are going to add D1 with 80. So we're adding a data register with an address register, which you can do. Okay, and the destination is the address register. So D1 has got the 102. So with A1, which has got the 1000, and the result is the 0502, which, if you notice, we had, sorry, I said it wrongly, D1, which had the 102 and 280, that's what we added, and it had the value of 400, okay? Now we're going to add D2, so the 1, 2, 3, 4, 5, 6, 7, 8, to A1, to the 1000. So the 5 should change to 6. Okay, and because it was a word, it became 6678. Now we're going to add the 1, 2, 3, 4. It's a long word, okay, to A1. So notice that we edit a long word. Now address registers are always, you're always working in 32-bit, okay? What I want to show you here is, and I will show it to you, so we're going to move 0 into 80, okay? Now we're going to add .w, okay? Notice that I do not have the add A, okay? And we are moving 8216 into, not moving, adding to what there is in 80, that value. So notice what happened. Because it's an address value, there is the sign extended, okay? I didn't read the note that there is, and I'm going to exit and go to the editor here, where I say there is a note here. The source is sign extended before it is added to the destination. Basically, when you are using an add, which is a word, because addresses are always 32-bit, it extends the bit depending on the value that we have. Because that value was 8216, then it extends the bit, the high bit, to the rest of the bits. So it becomes FFF 8216, okay? And what I want to show you also is, let's do A again. A and D. Notice that here I didn't specify add A, but I wrote add. But the assembler converted it into add A. Okay? This is normal. Okay? So although we write add, it does it does that. Also remember, as I said, and you will be fooled into this, okay, many times. When you're using the add instruction and it's a word, there is the sign extension. Not extension, extend it. Okay? Because this value is an 8, so there are 4 F's in front of it, as we saw in the example. So if I do it again, I'm just going to skip these. Notice we cleared 80, and notice what's going to happen to 80. We're going to have 4 F's, 8216, because we did add dot word. I constantly want to say move. So that's a pitfall. I didn't cover this last time, okay? So I didn't go into this detail. Now we have the immediate, okay? The immediate also works on a byte word and long word, okay? And give me a second, I need to update here. Why is this showing like that? Okay. The add immediate is to pass a value basically to a register. Okay, whatever that register is, not to pass, but to add a value to a register. Oh my god, today I need to say move by force for some reason. So you will see that in these examples, the values, so we move dot word 1 2 3 4 into the 0. So the 0 is going to have 1 2 3 4. Notice that the assembler didn't clear the high word, so it remained as 1 2 3 4 also. Then we're going to add a byte to the 0. So the last byte is going to change. And you saw it coming 68. Now we're going to add a word. So 200 to the 0. And you saw it changing in the last word. Okay. Now we're going to add a long word. Okay. Of 1000. So the 1 should become 2. Okay. And now we're going to add, okay, a long of F000 into the 0. Notice notice that once the next add instruction, which is the FFF 1000, comma the 0, notice what it's going to do to the carry. You can see that the carry flag was set, okay? Because we need to borrow, basically, to have the value, the actual value that we need in the 0. So the carry was set. And now we're going to add 1 to the 0. And I will show you this in a minute with the D command. Notice I do not have I specified, but the assembler will insert I because we are adding a value, basically. Okay, so the last one here, you can see that it added, the assembler added the I. Add quick. So the add quick is a bit different than the move quick, what you might know with, or what we have learned with move quick. So do not mix them, okay? They have different things. The add quick can only take a value between 1 and 7, okay? Sorry, 1 and 8. So basically it can add very quickly small numbers. It takes less memory, etc. Let me see if the difference between move quick and add quick is that move quick, I said, okay, Dario, go and dance. I want to see you dancing then. Because I do have the I do have the thing on the mobile, and they're showing the people dancing. But okay. Um. So I was saying, um, move quick works always is always on long words. Okay, it's always a long word, but move add quick can take word, can take byte, and can take long word. So sorry, I should have said them byte, word, and long word as per my screen. Okay, as you see per my notes on the Amiga. So let's go through the examples. So we move byte into the 0. So the 12 went into the 0. Okay. Notice we're going to add quick. We did not specify it, the size, so it's a word. Okay. Of 7 into the 0. And it went into 19. Notice now we're going to do a move.long. Okay. And it is of the value of 400 hex into 80. Okay. Notice now we're going to do add quick, okay, of 6,80. And notice we didn't specify the dot word, okay? Now, this is an address register, okay? So it will always work as 32-bit. So that 6 is going to increment on on the whole address, not on the last 4, not on a word, basically. Okay, and now we have add quick.long, but this time the destination is a D0. Is D0 is a data register, so whatever value we have in D0, we're going to add 8 to it. Now, what I need to show you is where we had add quick without specifying the size. And notice it always added the dot word because we did not specify the size. If we had move quick, it will always be long. So do not mix because it's quick. Maybe you think, okay, this is the same like move. It's not. Okay, the move quick can only support long, while add quick supports byte, word, and long word. Ah, hello Ozzy. Ciao, buona Pasqua Ozzy. So, I'm glad you're not working, Ozzy. I thought you were going to work this evening also. Um, anyway, I was joking a bit with Ozzy earlier on, but yeah. uh, hello, honey. I didn't know you're here, but yeah. Buona Pasqua anche a lei. Cool. Yeah, 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 yeah. The bot is working. It gave a shout out to honey without me doing it. It's cool that it does these things. Anyway, so let's read the next example. Now, this is the Docster example. basically he's saying the same things. He, in his example, Docster only covered add and add quick. Why? Because normally you write add and the others are added automatically. So the add A is added when you have a destination of an address register, and the add I is added when you are specifying an immediate value. And add is normal, which when it's a data register. So also Docster in his notes is saying that add quick uses 3 bits to have a value from 1 to 8, okay, and that add quick works on byte, word, and long word, same as add basically. So there is my value that is at the end of this source, which has a value of 1, okay, so just not 2. So we are moving 1 into 80. So my value here doesn't have a hash symbol in front, so it's not the label address, but the value that is at that label. So 80 should see 1. Okay, then we're going to do add quick of 8 into 80. Notice the add quick is a word, but the destination is an address. So that will work on the whole address. Now I have move.long 80, comma my value. So what we have in 80, the 9, we're going to store it at the label my value. We are taking that 9 that we have at my value and put it into a 1. Okay, as you can see, now 80 and A1 are the same. And now we're going to add .long 80 with a 1. And it becomes 12. A1. Now we're going to add 1 to the 0. Not add, sorry, move 1 into the 0. And we're going to add what we have in the 0 to A1. And it's a long. Okay, we ended up with 13. I think it's quite self-explanatory, this example. So we finished the add and we're going to do the sub. So sub is for subtraction, of course. So let me sort out here. So sub in a way is similar to add, okay, where we add the source, sorry, where we subtract the destination. Hold on, destination minus source, where we subtract from the destination the source. Okay, I needed to say this properly. So if I had to have like here the 0 and the 1 is subtracting the 0. It's not the 0 subtracting the 1, but the 1 is subtracting the 0 and the result is in the 1. Okay, so destination minus source. Okay, not source minus destination. That's very important, because when it's plus, it doesn't make a difference, but in a minus, it does. And of course, the result is in destination. Sub works on data registers, so address to data register or data register to address. It can work on byte, word, and long word. And basically, it affects all the flags, the conditional code flags. Let's see the examples. So we are moving. Ozzy is in the hype of the revision. He's calling Amiga. So we move 1000 into the 0. We move 101 into the 1, and notice they are words, okay? And we move .long into the 2. AGA is cheating. Where are you? They haven't yet used AGA. I'm trying to, while I am talking, I'm looking also at the screen, trying to locate Dario. But anyway, because he said he's going to dance. So yeah. But so far I haven't seen him dancing on the floor. Anyway, now we do sub. We subtract what's in the 1 to the 0. So we subtract, okay, the 101 from the 0 where we have the 1000, and the result is in the 1. I do not have the sound on, so yeah. And notice that the 1 ends up with 101. Because what did we subtract? It was a byte, okay? So I should have read 0, 0 for the 0 and the 1 as 01, okay? So 01 minus 0 is 1, no? So now we do sub, but this time is long, and we do the 0 to the 2 minus the 2, and the result is in the 0. And you can see that we ended up with a negative number, and because of that, notice the carry flag was set and the negative flag was set. No, I don't know him. Well, I do not know him. I heard the name. I think you mentioned it. Him. You mentioned him to me, but I do not. Yeah. And now we do, and notice it's a word. So D2 minus D1. So D2 where we have the 5, 6, 7, 8 minus D1 where we have the 101. And this time the 6 should become 5, the 8 should become a 7. And there you go. And that's the first example. We have the sub A, okay? Sub A is the same like add, as I said before, okay? But it is, I need to update my notes here. That should be I can update it here, and then it should be destination minus source equals destination. I mean, I'm not going to read the file, but I'm correcting the notes. Sub A, the destination is always an address. And remember, sub works on word or long word. So, again, when you do specify word, it is sign extended, okay? So be careful of this. And we are going to see another example. So I mean, the sign extended is always when you make mistakes. Let's say that, unless you're careful. So we're moving word 102 into D1. Okay, and we're moving the 1, 2, 3, 4, 5, 6, 7, 8 into D2. And we are moving the 400 into 80. Okay. And now we are moving, and notice it's a word, 1000 into A1. Now we are going to subtract from 80 what is in D1. Okay, and the result will be stored in 80, and it's a sub long, and we ended up with the 4002FE. Okay, now notice this is a word. So what's in D2? Okay, so A1, right? So the 1000 minus D2, that's a big number, but a word, so the 5, 6, 7, 8. So notice what's going to happen in A1. You can see that we got the sign extended, okay, because we subtracted, okay, and the value became negative, and when it became negative, it also copies the bit, the high bit, to all the rest of the bits. I'm going to show you exactly the sign extended bit. So we are moving this value, the 4Fs 8000, sorry, into 80. You can see it there, and notice we're going to move, and notice it's a word. It's a shame I cannot scroll. I do that. Notice that because we moved 8000, that has the extended bit F. So what we actually moved was FFF, so 4Fs 8000. And because we did sub.w, what we actually subtracted the value what was there with what we moved, and it became 0. You can see that 80 is 0. So be careful of this sign extended part, let's say that. It will catch you, I'm telling you. So now we're going to do sub I. I forgot to save this. Give me a second. And we do sub I. So sub I, works on byte, word, and long word, and it subtracts the source, which is an immediate value, from the destination. Okay, remember, the destination is always minus the source. Okay, so we're going to move 1 2 3 4 into the 0. We are going to sub immediate byte. Okay, so it's a byte what we are going to work with. So the 0 has got 3 4, and we are subtracting 3 4 from it, so it's going to become 0. We're going to work on word, and again sub I.W, so 200 from the 1200 that there is in the 0, so it will become 1000. And now we're going to sub dot long 1000 from whatever value we had in the 0, because when we started it was not 0. Okay, so it's going to end up with EDCB, I assume. There is saying 0, but we didn't start with 0, so yeah, we ended up with 0 in the last word. To be fair, this example should be corrected by having a clear the 0 at the front. Clear dot long 0. And I'm just going to show you the last part, because that's yeah. So now, okay, the last one, look, we have 1000, and we're going to sub dot long 1000. Okay, so it becomes 0. That's how so I had a typo there, or not, a missing instruction, let's say that, in my example. Which now is corrected. Sub quick. Sub quick is same as add quick. So basically you have the values from 1 to 8 as quick subtraction. Okay, and it's also destination minus the value that you specify, the literal, equals destination. So I'm just correcting it here. In both examples I had the issue, but it's okay. So it works on byte, word, and long word. Okay, so 1 2 3 4 into the 0, sub quick, and notice I didn't specify the that it's a word. Okay, so it subtracted 4 from the 0. I'm going to start again just to subtract. So from the last word, it's going to subtract 4 from the 0, and now it's going to move dot long the 44, the 400 406 into 80. Okay, so that's an address register, and notice it's sub quick immediate 6 to 80, so it's going to become 400 400. And now we're going to subtract 8 from the 0. So the 0 we have 1 2 1 2 3 0. okay? And we're going to subtract 8. And it becomes 1228. I mean, notice we also worked on a word. So just to show you that we worked on a word, you can see that the assembler added in all instances the word when we did not specify it. Okay? For me, I also made a mistake here, which I'm going to correct. D0 should be also be cleared, just for the sake of being consistent. So, just to make sure. Yeah. So I like that the example always start as it should. Okay. Last example that Docster wrote. Okay. Something wrong. Of what? Yes, I can repeat last example. Smooth quick. Sorry, at sub quick. Oh my god, today. Come on, AD. Okay, so we cleared the 0. Okay, we have nothing in it. We move 1, 2, 3, 4 in the 0. Right? Then we subtract 4 from the 0. It's a word, so it becomes 1, 2, 3, 1, 2, 3, 0. I have a typo there. And now we move dot long the 4000406 into 80. You can see it there, and we subtract quick, okay, dot word. So there is a dot word there, even though it's not shown, of 6 from 80. So it ends up to be 4000400, right? And now sub quick, but it's a dot word, okay, of 8 from the 0. So it's going to become minus 8. Forgot the value, but yeah. Where is the problem? It becomes 1228. Where is the problem? Because you're seeing 1, 2, 3, 4 minus 4 minus 8. I mean, we started with 1, 2, 3, 4, and then we subtracted 4, and then we subtracted 8. That's why we end up with 1, 2, 2, 8. Should be 1, 2, 2. Why? It's hex. It's 16. There is F, E, D. Ah, okay. No problem. Let's do this example. The Docster example. Come on. Okay, so we're going to move my value into 80. I believe there's a 1 there. Let me check. Oh, there's 13 hex. So 80 is going to be 13. Yeah. And then sub quick, but notice that that's dot word, okay? So minus 8, okay, from 80, it becomes OB. Okay, and then we move what we have in 80 into my value. So we move OB into my value. We load my value into A1. You can see that it's OB, and then sublong 80, comma A1. So basically we are going to subtract 80 with A1. It becomes 0, no? A1. And now we move dot long 1 into the 0. Okay? And then we sub dot long the 0, comma A1. And as you can imagine, okay, because we subtracted what's in the by 1, what was in A1, we ended up with all F's. No, because it's a -1. I'm going to show it again. Maybe I was not clear because of that thing. I'm going to do something so that that doesn't affect. Where is it? I'm going to do this. And do it again. Let's read it. AD. So last bit here, we're going to move 1 into the 0. Okay, and now, okay, remember A1 is 0. So -1, what's going to happen? It's going to become -1. So all F's, because we have like an overflow in a way. But because it's an address register, the flags are not affected. Okay? And that's basically the example. Oh. I'm behind, yeah? A lot behind. White cape file error. Ah, okay. Let's switch to here. So you should be able to see a visual code. Is it readable, the text? Houndock, is it readable, the text as it is? Not much? Okay. Is it better? Okay, cool. So I need to explain a bit about signed and unsigned numbers, or unsigned numbers and signed. just so that you understand how the CPU will handle them. This text was written originally by Docster, edited by me, but in essence it's Docster's. Okay? And he says today we talk about signed and unsigned numbers. In the maths world, we do see negative we do see negative numbers. This part will tell us how, so basically we see the minus sign, no? How, whether the number is positive or negative. I was going to read it, but I realized I better not. Okay? So, unsigned numbers. Okay? We all agree that the lowest number in a byte is 00. Okay? And the highest number is FF. Remember, we're talking on bytes. Okay? For a word, okay, the lowest number is 0000 and the highest is FF. And this continues for long word, quad word, whatever. Okay? Because we do not have a sign, okay, we refer to this type of numbers as unsigned numbers, or always positive numbers, let's say that. Now, signed numbers. Sooner or later, as Doctor says, you will be dealing with negative numbers. This is where signed numbers comes in, where we actually have the sign. Okay, so a byte of data assigned is from 0 to 7F is treated as positive number, while from 80 hex to FF is treated as negative number. Remember, we are talking on bytes. It's very important that you keep this in mind. Okay, so unsigned numbers we have from 0 to FF. Okay, lowest number is 0, highest number is FF. Signed numbers, okay, here is our 0, 0, it's in the middle. Positive, we have, positive we have till 7F, and negative we have till 80, which means FF is -1, FE is -2, etc. And he is showing it here. So 0 is here. Okay, this is the positive side and this is the negative side. Okay, this process is known as 2's complement. Okay, and it's the idea of using the most significant bit to signify the value, whether it's a negative or a positive value. Okay, so this bit. Please remember that I'm still talking of bytes. Okay, all numbers from 80 to FF will have this bit set. Okay, for negative numbers, while the positive numbers will not have this bit set, which will be 0 to, which will have the bit always 0. Okay, for word or long words it's the same. You know, the highest bit is always indicates whether it's a positive number or a negative number. However, do not confuse byte. Do not expect to have word to be the same behavior as byte or long word. Okay, so it's very important not to confuse byte, word, or long word. As shown above in the plus/minus table, we know that the byte FC equals 2 minus F4, -4. But we are talking about bytes, okay? But if you were to read, okay, FC as word, okay, which is 00FC, then the number will no longer be negative. Okay, it becomes a positive number because we are talking about words. Why this is important? Because when you have unsigned numbers, you need to make sure that the size of them is always the same. Do not mix the size. So in a word, the positive numbers are from 0000 to 7FF. To get -4, you will need to extend the word to FFFC. Okay, or for a long word, it becomes FFFFFFFC. So let us be clear. I'm reading exactly what Docster wrote here. Changing the most significant bit will not convert it into a negative or positive number directly. Setting the most significant bit, however, will give us, okay, a value will give us 1000 or 0100, which is 84, while 84 in a negative number, it is -4. It is in fact -7C. So this, I think this sentence is confusing of Docster. Let's be clear. Which is important is here, what he said here. Let me see if I can change the English here. Because here he says changing the MSB, they're setting the MSB. Nah, this is going. No, let's, I think this I'm going to remove. So negative numbers starts, now we're talking about a byte again. Negative numbers start from FF, which is -1, and proceed downwards. Okay, so FF, FE, FD, FC. Which line? Tell me always the line number. 69. Vice. Vice versa, no? So, oh yeah, oh crap. So, this is, of course, there is of these are, of course, a simpler method to convert a number from positive. Okay, so here there is, of course, a simpler method to convert from positive to negative and vice versa, which can be done by performing a logical complement onto the number and then not, so basically using the not and then add 1 to the number. So let's see how he did it. There is of course a simple method to convert a number from positive to negative and vice versa, which can be done by performing a logical complement, logical complement on the number. Okay, I got it. Using the not instruction, which can be done by performing the logical complement is not really right word there, which can be done by performing here it's okay. This can be achieved using the not instruction and then add 1 to the number. This sentence I'm not happy. Or to be honest, it doesn't need to. Doesn't even need to be there. Yeah. There is of course a simple method to convert a number from positive to negative and vice versa. This can be achieved using the not instruction and then add 1 to the number. Yeah. I know what he wants to say here. So let me just add a sentence or two here. To convert a number from positive to negative number, it is not enough to change the most significant bit of that number to have a 2's complement number. That's what he wanted to say with that sentence. And then I should say, to do this, there is a simple, I'm going to remove the of course. That makes more sense, I think. So if you're dealing with negative, let's take the addition and subtraction, okay, for now, because we haven't done the, division and multiplication. If you are dealing with signed numbers, okay, then you need to check, okay, for the sign, for how to say, when you're doing the addition or subtraction, about the sign, okay, you need to take care of it. But when you're doing multiplication and division, you don't. You need to make sure that you're using the right instruction. Okay. Now earlier I made a small mistake saying you need to always use the right instruction, but I was referring to division and multiplication, I have to say, because you do need to be careful there. Else you have to always check for the a negative flag and for the overflow flag. Negative flag tells you the sign, and the overflow flag is when you subtracting something and it overflowed, so you get the negative number basically. I hope that explains it. So I must know that if that value is the result of you need to check. Yes, if you are dealing with signed numbers, you need to check for the value whether it went positive or negative. But the thing is, the 68,000, we haven't covered them, okay? The 68,000 have the compare instruction, okay, which can take a lot of things, and the compare instruction can work with signed numbers and non-signed numbers also. So yeah, I just wanted to cover signed and unsigned numbers so that one can realize that one, there are different instructions and for these type of things, and two, okay, not to mix. If you're working with words, you continue working with words. If you're working with byte, you continue working with byte. You don't switch between one and the other. That's the main thing right now. Yes, it's context related. Here, in fact, if I had to, he has some examples, okay? And actually, he had one example and I added a lot of examples. So we're going to clear the 0, okay? We're going to move 4 into the 0. So here we are working on byte, okay? It's a byte. And we're converting the 4 to -4. To convert it to -4, first you do a not of what we have in the 0. So it becomes FB. And then we add 1 to it. I need to go on the Amiga. Let's start it again. So to convert from a number to make it 2's complement, okay? If we have 4 and we want to make it -4, okay, we're clearing the 0. We move 4 into the 0, okay? We not, and remember, we're working on a byte, okay? So we not the 0, and it becomes FB. And then we add 1 to what's in the 0. And that becomes -4. Again, okay, we are going to convert it back into 4. So we not B, it becomes 3, and then add 1. That's the method to convert from one number to the other. Same for word, okay? Clear the 0, 4 into the 0, not dot word, the 0, and it becomes FFFB, add 1, and it becomes FFFC. Converting it back, we do a not and add 1. Same thing for long word, okay? We clear the 0, we put 4, we not the 0, and you can see all the F's now, FB, and we add 1, it becomes FC. To get it back, not the 0, add 1. Basically, you always have to follow the not and add thing to convert from a positive to a negative and vice versa. This is what I wanted to show, and also to show you that you need to keep the same size. It's very crucial, the same size, very crucial. So that's all I had about signed numbers. Let's do the multiply. Now, the first example that I have is multiply unsigned. MULU. Okay? And it takes a value, okay, and multiply it. So destination multiplied by source result in destination. Okay, size is always word. Okay, if you specify a long word, it will still work on word. Okay, so it's a word times a word, not a long word times a long word. The result is in word. Okay, so this is why you have destination times source equals destination, and notice size is word, but the result is a long word. The 68,000, not higher processors, because there are other instructions in higher processors, can only work with words, okay? Cannot work with long words. The result is always in a long word. So 16-bit word, as it says here, to 32. So 1000 into the 0, multiply unsigned, so what's in the 0 with 223, and the result is in the 0. And you can see we have the long value of 223000, of course, because we multiply it by 1000. Now we're going to move 8000, sorry, into the 1. Okay, notice that we are going to use word, so only the 8000. So what we are going to do is 8000 times, so the 1 is 8000 and the 0 is what right now? The 223000, sorry, the 3000. Okay, so it's 8000 times 3000. That's what we're going to multiply with. So be careful of this. You'll always work in words. And you can see it. We've got 18,000. 18,000,000,000. Okay. If I do, you can see that multiply, okay, unsigned is word. Okay. What the heck happened? Okay. So, continue. Now we're going to do signed. So for signed, okay, is the same thing. Word is the source, word is the destination, destination times source equals destination, but destination is long. So multiply signed numbers, okay? So we still, source and destination are still word, okay? We can have destination as a minus, we can have source as a minus, or we can have both of them as minus, okay? But using 2's complement numbers, okay? The result is in a long word. We're doing multiplication, so minus times plus, or we can have plus times plus, so still long word. So yeah, so same as before, but we can have negative and positive numbers in the word. So we have 1000 into the 0. Okay, we are multiplying that 1000. Okay, and you notice we're using the signed version, MULS. Okay, with 2 to 3, so we get as before 2 to 3 0 0 0. Okay, now remember we have signed numbers, so we're going to move 1000, sorry, not 1000, 18,000 into D1. Okay, but we are going to work with words, so D1 will have the value of 8,000. That is a negative number. Its most significant bit is set. Okay, so we're going to multiply, okay, the negative number that we have in D1 with what we have in the 0 with the 3000. Okay, because remember we're working on words, and we end up with E8 0 0 0 0 0 0. Again, to complement, so that was the first example. Second example, where we have when we work with negative numbers, and notice the previous result set up the negative flag. Okay, again we're moving FFCA into the 0, so we have a negative number into the 0. Okay, and we are going to multiply that negative number by 10. Okay, so FFC0 is minus 40. Minus 40 times 10 is minus 400. That is the FFFFC00. I hope that is clear that we were working with 2's complement numbers. And remember, it's always a word. Although I always tell you to specify here dot word, I have to say, I do this. I didn't do it here because I want to show you. I mean, you cannot do dot L, okay, as I did here. You can only do dot W, okay? Come on. But what I wanted to show you is when you do A, D, it converts the number, the size into word automatically. Okay, so it adds it automatically, like I was showing you before. Come on, today. I'm just going to read it again because I changed it, and I'm going to show you. Okay, so look, there is no dot W, okay, or dot long or whatever. Actually, you cannot have dot long, but anyway. And if I assemble it and then debug it, sorry, disassemble it, you can see it added dot W. So we have another example by Docster. Okay, let's see it. So he clears the 0 and the 1. Okay, then we move 10 into the 0. Then we move 2 into the 1, which is a word. Okay, and then we multiply. Okay, and this is sign, so the numbers are both of them positive. 2 times 10, basically, which is 20. Okay, always hex. So Docster didn't go into the signed numbers himself, but even though he used MULS, but to show you that with MULS you can also use positive numbers. We'll stop here, but yeah. So guys, thank you very much. Happy Easter again to everyone. And we'll continue next week. And I will have better examples related to this one. See you guys. Bye-bye.